Sometime in November 2026, a signal will leave a spacecraft traveling through interstellar space and begin the longest single-direction journey any human communication has ever made. It will travel at the speed of light, 186,000 miles per second, for exactly 24 hours before it arrives at Earth, one light day. The spacecraft that sends it is Voyager 1, launched in 1977, currently 15.8 billion miles. From home, moving through territory, no human instrument has ever mapped at a speed of roughly 38,000 miles per hour. When that signal arrives, when humanity receives the first transmission ever sent from a distance of one light day, it will carry data from a place so remote that the sun appears as nothing more than a faint star in the darkness. And it will almost certainly be one of the last scientific signals Voyager 1 ever sends. Not because the spacecraft is breaking down, not because the mission is being canceled, but because the power source that has kept Voyager 1 alive for 49 years is running out of energy, instrument by instrument, system by system, and the team at NASA's Jet Propulsion Laboratory is right now making the hardest decisions of the mission's history. Decisions about which of Voyager 1's last functioning eyes to close forever in order to keep the remaining ones open a little longer. The transmissions. Voyager 1 is still sending home, from the edge of everything humanity has ever reached, contain data that scientists are calling irreplaceable. And what that data is showing about the space between the stars is, in the most literal scientific sense, stopping the world. The power crisis that is defining Voyager 1's final operational chapter is the unavoidable consequence of physics. The spacecraft runs on 3 radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium, 238, into electricity. When Voyager 1 launched in 1977, those generators were producing approximately 470 watts of electrical power. Every year since launch, as the plutonium has decayed, the power output has dropped by roughly 4 watts. By April of 2026, available power had declined to approximately 220 watts, less than half of what the spacecraft had at launch. Of those 220 watts, a significant fraction goes to heating critical systems against the extreme cold of interstellar space, where temperatures approach negative 270 degrees Celsius. What remains for actual science instruments is a thin margin that has been forcing the mission team to make painful choices for years. Voyager 1 shuts off an instrument to buy time before what engineers nicknamed the Big Bang Fix, a potential upgrade that could allow the record-breaking probe to continue exploring deeper into space and perhaps even restart some of its science instruments. The instrument that was shut down in April 2026 to buy that time was one of the last remaining science systems, a heater that had been keeping one of the cosmic ray detectors within operating temperature range. The team calculated that the instrument itself could survive the cold without the heater, even at temperatures far below what it was designed to handle, and that the power saved from turning off the heater could keep the instrument running for longer than it would if the heater continued to consume the power it needed. It was a gamble. And as of the most recent mission status reports, the gamble appears to be working. The Big Bang Fix that engineers are working toward is an attempt to do something that has never been done with Voyager: remotely reprogram its onboard computer systems to squeeze more operational life from hardware that was designed in the early 1970s. The 2023 memory chip crisis, when a corrupted chip in the flight data subsystem caused Voyager 1 to transmit gibberish for 5 months before engineers painstakingly rerouted its code through other memory locations, demonstrated that the JPL team can perform almost miraculous engineering feats on a 49-year-old spacecraft from 15.8 billion miles away. The Big Bang Fix is even more ambitious. It involves identifying new efficiencies in how Voyager 1's computers allocate their remaining power budget, finding ways to keep more instruments running simultaneously than the current configuration allows, by redistributing power demands across different systems in a more optimized arrangement than the original mission architects designed in 1977. If it works, Voyager 1 may be able to keep at least 3 science instruments operating well into the 2030s. If something goes wrong in the reprogramming, if an error in a command sent from Earth corrupts a critical system, Voyager 1 could go silent immediately and permanently. There is no backup. There is no second chance. Every command takes 22.5 hours to arrive at the spacecraft. Every response takes 22.5 hours to return. A mistake discovered on Earth takes 45 hours to even begin being corrected, and correction may not be possible if the damage is severe enough. The Big Bang Fix is the highest stakes software update in the history of spaceflight. What makes the urgency of those final transmissions so acute is what Voyager 1 is currently detecting in interstellar space that no model predicted. In November 2026, the probe will reach 1 light day from Earth, 16 billion miles away, and the data it sends back from that distance continues to challenge what scientists thought they knew about the space between the stars. The most recent scientific results from Voyager 1's plasma, wave subsystem, one of the instruments the team is fighting hardest to keep operational, show that the electron density of the interstellar medium around Voyager 1 has been increasing steadily as the spacecraft moves deeper into interstellar space. This was not expected. The standard model of the local interstellar medium predicted that the electron density would be relatively uniform in the region immediately beyond the heliopause, varying only gradually over large distances. What Voyager 1 is measuring is a systematic increase, a gradient in the plasma density that suggests the spacecraft is approaching a region of higher interstellar medium density that the pre-Voyager models did not have enough information to anticipate. Kinetic models published in 2024 and 2025 now predict that both Voyager spacecraft are approaching a maximum in plasma and neutral atom densities at approximately 200 to 250 astronomical units from the Sun. Voyager 1 is currently at approximately 167 astronomical units. It is, in other words, approaching the maximum of a density enhancement that no instrument has ever measured in situ before. The data it sends back from that region, if it can keep its instruments operating long enough to reach it, will be the first direct measurement of a feature of the local interstellar medium that theorists have predicted but never confirmed. The cosmic ray data that Voyager 1's cosmic ray subsystem has been returning since its heliopause crossing in 2012 has produced results that connect directly to the question of how well protected life on Earth actually is. Inside the heliosphere, the bubble of solar wind that surrounds our solar system, the Sun's magnetic field deflects and scatters a significant fraction of the galactic cosmic rays that would otherwise bombard the inner solar system continuously. When Voyager 1 crossed the heliopause, its cosmic ray detector registered a dramatic and immediate increase in the flux of galactic cosmic rays, particles accelerated to enormous energies by supernovae, pulsar wind nebulae, and other violent events throughout the galaxy. The increase was not gradual, it was a step function, a sudden jump from the shielded interior of the heliosphere to the unshielded interstellar environment in a matter of days. And the cosmic ray flux in the interstellar medium immediately outside the heliopause was significantly higher than pre-crossing models had predicted, because those models had overestimated the thickness and effectiveness of the heliosheath, the turbulent outer layer of the heliosphere, as a cosmic ray barrier. The implication is that the heliosphere provides somewhat less protection against galactic cosmic rays than scientists had assumed. Life on Earth has been evolving under a cosmic ray flux that is determined by how well the heliosphere shields the inner solar system. If that shielding is less effective than models assumed, the actual cosmic ray environment that has shaped Earth's biological evolution is different from what the calculations predicted. The magnetic field measurements that Voyager 1 has continued to make since its heliopause crossing remain the most theoretically challenging results the mission has produced. The magnetic field in the interstellar medium immediately beyond the heliopause is parallel to the magnetic field inside the heliosphere, a result confirmed by both Voyager 1 and Voyager 2, crossing at completely different locations, ruling out any local geometry effect. Standard models of the interaction between the heliosphere and the local interstellar medium predict that these two fields should be oriented at a significant angle to each other, because the interstellar magnetic field and the solar wind magnetic field have different origins, and the heliospheric boundary should not perfectly align them. The confirmed parallel orientation across two independent crossing points is a result that heliospheric physics has not been able to fully explain in the years since it was first measured. Papers continue to be published attempting to model the interaction in ways that reproduce this alignment, but none has yet produced a fully satisfying physical explanation that is consistent with all of the other Voyager observations simultaneously. The thermal pressure anomaly, the fact that the interstellar plasma immediately beyond the heliopause is hotter than predicted, connects to the magnetic alignment in ways that are still being investigated. If the magnetic field alignment is maintained by a process that continuously converts magnetic energy to thermal energy at the boundary, a process called magnetic reconnection, that process would add heat to the plasma on both sides of the boundary, potentially accounting for both the measured temperature excess and the measured field alignment simultaneously. But the scale of the energy transfer required to produce the observed temperature excess at the observed plasma density is larger than standard reconnection models at heliopause scales predict. Something is adding energy to the interstellar medium at the solar system's boundary in amounts that exceed what the models account for. That excess energy, wherever it comes from, is the most recent entry in the list of things Voyager 1 has measured that science does not yet have a complete explanation for. As of January 2026, both Voyagers are more than 13 billion miles from Earth. The team is hoping to keep the cosmic ray subsystem running on Voyager 2, as well as the magnetometer and plasma wave subsystems on both spacecraft, enabling both probes to essentially function like weather stations in interstellar space, sensing the environment they travel through. weather stations in interstellar space. That phrase used by Voyager project manager Susie Dodd captures what the mission has become in its final years. Not the exploratory flyby of the outer planets that it was designed for, but a long-duration in-situ measurement campaign at a location that no future mission will reach for decades. There is no successor to Voyager currently planned that would reach interstellar space in any timeline relevant to working scientists today. The Interstellar Probe concept, a mission specifically designed to explore the outer heliosphere and interstellar space, has been studied extensively by NASA and was given the highest priority ranking in the 2023 Heliophysics Decadal Survey. But it has not yet been approved for development, and even if it were approved, today it would not launch until the 2030s at the earliest, and would not reach interstellar space for another 15 to 20 years after launch. By the time any successor arrives at the heliopause, Voyager 1 will have been silent for decades. The data Voyager 1 is sending home right now, from 15.8 billion miles away at 22 watts of transmitter power, arriving at Earth as a signal 20 billion times weaker than a mobile phone, is irreplaceable. It is the only data humanity has or will have for a generation from the space between the stars. The November 2026 one light day milestone will not produce a new image. Voyager 1's cameras were turned off in 1990 to save power. It will not produce a dramatic announcement or a stunning visualization. It will produce a data packet, encoded telemetry from aging instruments on a 49-year-old spacecraft, arriving at the Deep Space Network's large antennas in Goldstone, California, after a 24-hour journey at the speed of light. That packet will contain measurements of cosmic ray flux, plasma wave oscillations, and magnetic field strength from a distance that no other measurement in history has reached. The scientists who receive it and analyze it will publish papers. The papers will be read by other scientists. And the knowledge embedded in those measurements about the structure of the interstellar medium, the boundary of our solar system, the cosmic ray environment that shaped life on Earth, will become part of the foundation that future generations build on when they eventually send a mission specifically designed to explore the space that Voyager 1 stumbled into by surviving long enough to get there. The final transmissions of Voyager 1 are stopping the world not because they contain a dramatic revelation that changes everything in a single moment. They are stopping the world because they are the last data humanity will receive from the edge of everything for a very long time. And what they are saying, in the precise language of particle counts and field strengths and plasma densities, is that the universe beyond our solar system is stranger, more structured, and less understood than the models built without this data ever suggested.